so let's move on to the next talk. So the next talk, we have two presenters. Shuang is going to start things off, and then Thakkar will take over about halfway through. And the talk is on kind of related to the previous talk, looking at characterizing the clipping in gradient descent. So Shuang, take it away. And can't hear you.
Sorry, it's muted.
Okay, I think we can hear you now.
Hi, everyone. So, yeah, we're going to talk about our work characterizing private clip gradient descent on convex generalized linear problems. I'm Shuang, and this is joint work with Thakkar and Abhradeep Thakurta from Google. So suppose we have a dataset D consists of n examples, each has feature X, label Y, and we want to separate them based on the labels. We can use something like logistic regression and try to minimize the average loss over our examples in D, which we call the empirical risk. Of course, the setting also generalized to other losses, so we just call this term L theta D, where L is some loss function. If the loss is convex in some convex model space C, then there exists some true minimizer theta star. In practice, we might be using gradient descent or other optimization method to solve this problem. And if we further need differential privacy, we might be using algorithms like DPSGD, just as Matthew just mentioned. The algorithm will give us some model theta. The excess empirical risk of theta is defined to be the difference between the empirical risk of theta and that of theta star. So to analyze an algorithm, we can look at the expected excess empirical loss for the model it returns. So people always want to find what is the best possible algorithm with the smallest excess empirical risk. For differentially private ERM, prior work provide a matching upper and lower bound of the order square root P over epsilon, where P is the model dimensionality, epsilon the privacy parameter, and N the dataset size. But this lower bound for this problem is only hold for constraint problem, where the model is constrained in a set with bounded radius. And also there is no assumption on any structure of the gradient. So the question is, can we get better bounds if the problem is unconstrained and the gradient lie in some potentially unknown low rank subspace? One prior work look at this problem and get a bound of the order 1 over epsilon square root n using the objective perturbation and output perturbation. But first, the square root n term in contrast to the n term on the left is a little bit unsatisfactory. And second, the bound work only for a convex problem. And we also wonder what will happen for a non-convex case. So in our work, we look at a special class of...
Sorry to interrupt. Oh. There's a little bit of static on your microphone. I don't know if you could just try adjusting a little bit.
Okay, sorry.
It may not go away and we can continue, but I just thought if there's a quick adjustment, then that would be good. But please continue.
Sure. Does this work?
That's great. Yeah.
Yeah. Much better. Thanks.
So sorry. Does this work?
Much better. Thanks.
That's great. Thanks.
Oh, okay. Sorry. Yeah, so we look at a special class of problem called the generalized linear problem, or GLM, and analyze this differentially private gradient descent algorithm, or we call it DPGD. We show a bound for the excess empirical risk, as is shown here. Basically, the P term in the prior work is replaced by rank M, which is the rank of the feature matrix in the GLM problem. So obviously, this bound is dimension independent, is independent of the model dimensionality, is guaranteed to be better than the previous bound because the rank is always smaller than both P and N. We further show this is tight in a follow-up result with Thomas Stenke. Another feature about this bound is that it doesn't depend on the convexity of the loss as in previous dimension-independent bound. So it can be easily extended to the non-convex problem to analyze the first-order stationary point. We also provide some analysis for the case when there is gradient clipping in the gradient descent algorithm. We show that for convex GLM, we get the same bound as before, but with respect to another well-defined objective function, which might be different from our original empirical risk function. And if we clip so aggressively, then this new objective function might have a very different minima compared to that of the original function. Also, we show that for a problem which is not convex GLM, such as the multi-class logistic regression, clipped DPGD may not optimize any well-defined objective. Now let's look at the detail of our result. The algorithm we want to analyze is one of the very generic algorithm, the DPGD. First, there is some computer and some data set. The computer has its current estimation of the model theta t, and it will query the data for the gradient at this model. Here we assume the gradient to be the exact gradient instead of the stochastic gradient. And for privacy purpose, we assume the gradient of individual example has the L2 norm upper bounded by some parameter L. To guarantee privacy, we will be adding Gaussian noise to form a private gradient, G priv t, which is sent back to the computer. Then the computer will conduct a descent step, setting theta t plus 1 to be theta t minus eta times G priv t, where eta is some learning rate. So if there is some constraint set C, we will project the model back to this set. Then the computer will repeat the same process with the new model theta t plus 1. And finally, after many iterations, the computer will return a model as an average of all the models it has produced over the iterations. Although here we use the full batch gradient, we want to say that our bound can be easily extended to the differentially private SGD. So previous work shows that for convex ERM, DPGD would give an expected excess empirical risk of the order shown here. So the L is the gradient norm bound, theta star the true minimizer, P the model dimensionality, epsilon the privacy parameter, and N the number of examples. And so notice this P term here, we're going to improve upon it. As we have mentioned in the beginning, we'll be looking at a special class of optimization problem, the generalized linear problems. This is basically the problem where the laws depend on the label Y and the inner product between the model theta and Fisher X. It covers the cases like binary logistic regression and support vector machines. We call it convex GLM when the loss is convex and the constraint space is also convex. So here is our result. For unconstrained convex GLM, meaning the constraint set is basically the whole space, we let M be the projector to the eigenspace of sum of xi transpose, where xi's are the Fisher vectors of all the data samples in our dataset D. We can show the expected excess empirical risk is upper bounded by this formula. So basically, the rank of M replaces the model dimensionality P in the previous bound. Obviously, this bound is independent of the model dimensionality, and because it's always holds that the rank of M is smaller than both P and N, where P is the model dimensionality and the number of samples, the bound is guaranteed to be better than the previous two bounds, and is usually much better. The main technique we used here is that for additive Gaussian noise, the norm with respect to the matrix M, which depend on the rank of M, can be much smaller than the L2 norm. So a few points we want to highlight. First, the bound, it comes from exploiting the low rank structure of GLM. And second, the low rank structure is only used for the analysis. The algorithm itself does not need to change and does not need to know the exact subspace. And third, the bound is actually tight, and we can show this using fingerprinting code. So compared to prior work, which also show a dimensional independent bound for output perturbation and objective perturbation, our bound is not only better, but as we analyze DPGD, which does not require convexity to ensure differential privacy, our bound can extend easily to the non-convex problem. Also, our result can transfer to the local differential privacy setting to give the first dimension independent bound there. But the output perturbation and objective perturbation, they are intrinsically incompatible with the setting of LDP. There is another recent work which projects gradient to some known subspace and get a bound which depend on the log of the model dimensionality. But it need public data to know the subspace, while our bound does not require change in the DPGD algorithm. So now I will hand over to to talk about the non-convex GLM and clipped DPGD.
Thanks, Shuang. So we just saw how bounds, we just saw bounds for convex GLMs. Can we say something about non-convex GLMs? Such loss functions appear commonly in robust regression, such as Savage loss, tangent loss, and tempered loss. So in this work, we show that if the loss function is smooth, then DPGD converges to a first order stationary point, which is basically a point where the gradient of the loss is 0. This convergence is dimension independent in that it depends on the rank of the feature matrix, similar to the previous result. Our analysis goes via classic result by Nesterov that was restated in Zoo 18, which shows the first order convergence of gradient descent for non-convex objective losses. We conjecture that one can extend our result to second order stationary points under as additional assumptions on the loss. So earlier in the talk, we saw results for DPGD, but the technique crucially requires knowing the Lipschitz constant of the loss. This is difficult to know a priori in real world applications. In practice, a variant called clipped differential gradient descent is used, which bounds the norm of each sample's gradient by a prefixed value called the clipping norm, which we denote by B here. In particular, if the norm of the gradient exceeds B, then it is scaled down to B equal to B. So in this work, we characterize the clipping operation as a variant of Huberization for convex GLMs. We can visualize this via the following example. Here, the x-axis denotes the dot product of x and theta. The y-axis denotes the objective value. The solid line represents the function, and the dotted lines are what the function would correspond to after clipping. So here, the kinks are basically where the gradient value exceeds the clipping norm B. The first result we show is that for convex GLMs, clipped DPGD obtains dimension independent convergence to the minimum of a well-defined objective function. That is to say, we can precisely quantify the objective function that the algorithm optimizes. Moreover, we show that for functions that are not convex GLMs, the objective which clipped DPGD optimizes over may not even be well defined. We show this via an example of multi-class logistic regression, details of which you can find in the paper. Now, let us look at what could happen with aggressive clipping, which is when the clipping norm is much less than the Lipschitz constant of the loss. First, from the example of Huberization I showed earlier, it should be clear that clipping introduces some bias in the process. However, the question we are interested in is if good performance is guaranteed when you aggressively clip, and the answer is no. We show this via an example of logistic regression with n samples and assuming unit Lipschitz constant. We can show that the excess risk of DPGD is on the order of 1 over n, whereas if your clipping norm is less than 1/4, we show that the excess risk of clipped DPGD is lower bounded by a constant. And this is a degradation from the previous guarantee. There is also recent work that shows how clipping can prevent DPSGD from converging to a stationary point. So to summarize, for convex GLMs, we show dimension independent upper bounds for the excess empirical risk. And in follow-up work, and this is carried to Thomas Steinke, we show our bound is tight. Next, for non-convex GLMs, we show dimension independent convergence to first order stationary points. We also provide the first convergence guarantee for the common technique of clipped differential private gradient descent. And lastly, we explore some adverse effects of aggressive clipping. For more details, please look at our paper on arXiv. With that, I'd like to conclude. Thank you for listening, and we'll be happy to take questions.
Great, thank you both for your talk. Do you have a couple of minutes for questions? I know we're running a few minutes over into the poster session. Looks like Salil has a question.
Hi, and Shuang. Yeah, great talk and really interesting. So on the last bit about the aggressive clipping, are any ideas on um, what alternatives for dealing with this issue may be if we are in a situation where you can't compute the Lipschitz constant? I mean, of course, one is to use a very large B, but that has a big cost. Are there many settings in which one maybe can estimate in a differentially private way what the clipping bound should be, or other approaches to this issue?
Yeah, great question, Salil. So while we say that aggressive clipping can hurt you in some instances, there are works which study, even though empirically, how can one go about setting the clipping norm in a realistic experiment. So like some examples are you could set it adaptively based on like some target percentile that you want not to be clipped, so that you at least get some, like almost all the information that they have. And there are experiments showing that setting it in various ways could be advantageous. Theoretically, I don't think we have the best understanding of how to go about it.
Another example I could add, so this is Abhradeep here, the third author of the paper. So another example we could add is if you change the activation functions, essentially that kind of controls the gradient norms. So in that sense, you do not like blow up the norm of the gradients during the training process. Something like instead of using ReLU kind of activations, you can use tempered sigmoids. So that's a poster we have in the poster session.
I see. Thanks.
Any other questions? I have a quick question. So there's been some work on like more exotic forms of clipping. I think there was a paper at TPDP last year by Reza Shakri and others about like only keeping sort of certain dimensions of the gradient and setting the others to 0. I was wondering if your analysis can be kind of extended to these more exotic like clippings or encodings of the gradient.
Not sure actually. I have to think about.
This is a good question.
Yeah.
Essentially, what I mean, the paper, in our paper, one can summarize in one sentence that if you have a very well-defined, well-behaved objective function, something like GLMs, then you understand exactly what clipping does. But when you are even in multi-class logistic, you'd get set of gradients would not even set of vectors which would not even conform to a gradient field of any objective function. So really weird thing starts happening even analytically. So I'm not sure if we could analyze this exotic forms of clipping in full generality.
Okay. Okay. Well, thanks guys for the talk. So that concludes the morning contributor talk section. And so the next thing on the schedule is the poster session. So for that, you will actually leave this Zoom call and walk through the gather space over to the poster session. And if you're presenting a poster, you just can move to your poster, find it, and stand on the orange carpet. And then when people, if you want to talk to somebody or hear about a poster, you just move onto the orange carpet, and a mini Zoom session will launch automatically for all the folks on the orange carpet. So thanks everyone, and look forward to seeing you over in the poster session.
You have to hit
Rachel.
X on the carpet to see the poster full screen.
Okay, yes, thank you. And then I think if you want to share your screen, there's like a beta feature that allow you to do that. So if you have like an updated version of your poster or some other thing you want to share, you should be able to do that as well. Okay, thanks everyone. I'll see you over in the poster session.